Hello and welcome to my channel. Here from the middle of the embedded world, behind me you can find a lot of companies with whom I'm gonna be interviewing, asking a lot of questions. We will be coming into detail describing their product. Maybe you will find the component of your project, or maybe you get an idea about the embedded system, the embedded world as a studying field or as a career, as a working for your careers. So stay with me, I will be showing all the secrets, and I will start by showing you the entrance because here you can see a lot of people are coming to the events from the whole world. I met people from north of Europe, from USA, from Japan, from China, from Taiwan, and the entrance is pretty cool. Even with some music and some DJ, I like that. So the vibe is very high, the weather is amazing. And it's time to go to the technical stuff. Let's come. So the first thing to be done in such an exhibition is, of course, to get all the information about the exhibition. Let's see. So I would like to speak with Raspberry Pi because there are a lot of people who would like to do a lot of things with Raspberry Pi. For me, NVIDIA, if I find it, I think it's here. It will be also interesting to see what kind of applications are done using NVIDIA. And Microchips, Texas Instruments, all of these companies I must go to speak with them, to interview them. But let's first see the vibe here. So firstly, the people are giving their stuff there. Yeah, NVIDIA, I can see the logo of NVIDIA. This is at the very beginning. Wonderful.
One of these ones.
So this is of course only the first impression, but for the embedded world, I think I'll look at this apple that is happening here. Did it discovered? I think it discovered, or if the apple is coming or something. I'm not sure, but there are a lot of stuff to be shown here. So the best thing to do is to get in contact with any of these companies, and hopefully we get an interesting information. But the very first impression is that there are a lot of stuff related to the computer vision. Well, I am here since few minutes, but yeah, it's a lot of stuff to be seen here. Let's see. Yeah, cool. And more to the applications of Intel. I can see a lot of applications here, and some chips and recognition. But something that attracts me very well is a robot arm. Oh, hi.
Hi, hello.
Would you like to tell me a little bit about this arm? It looks
Sure. So
looks like it classifies the objects here. What is actually doing?
So this is
it struggles even a little bit. Oh yeah, it's achieved it.
So it is a pick and place robot. So which identifies the objects which are running on the conveyor belt, and it identifies the right object and place in the right bin.
Okay, so what objects do we have? We have only 2 objects now.
So at the moment we have the cube and we have the gear. So
When it put the
right
gear in-
and right now we don't have the training part of the gear, so it only identifies the cube as a cube and identify gear as an unknown object.
Okay.
So now it should put in the unknown. So it is putting in the unknown because right now we are running the model which identify only one object.
Okay. Cube and gear. Perfect. Nice. And how stable it is? Wow, it's struggling with it.
Yeah, it is a round object, so
Okay.
Unbekannte Objekte haben, werden hier im Background abgespeicherte Bilder. Die kann man dann
So this platform looks like to start the arm. You see arms also, robots also struggles by somehow. Huh? But where is
Yeah.
the camera? I cannot see any camera.
so
here,
you can see the 2 cameras on the top.
Wow.
So one camera is Intel Real Sense camera, which is a depth sense camera, which captures the depth of the objects, and another is a 2D camera, which is a Basler camera connected over here.
Okay, I can see. Can I put my hand?
Yeah, absolutely. If you want to experience the safety, so you can hear. So once people's safety is enabled, so the robot gets slower
Okay. Yeah. I see.
because it identifies my hands and it is doing everything in the slow motion now.
So I am not slowing the video, guys. Yeah.
Yeah.
Okay, perfect.
And another is
nach dem Training besser einfach runterladen und dann distanzieren und dann
it can track your objects.
trainiert oder der Fehler drin ist. Also das hier ist Intel Geti, das ist ja der
It's following you now.
Yeah, it is following me. So if I have an object,
hier auch den
it can object.
Yeah,
like
good.
this.
But does it follow your hand or the object?
It is
So if you-
following the object.
Oh yeah, okay. So if you put your hand free, it will not make anything.
Yeah. Now if it is a smooth, then it is a smooth. So it is following my hand at the moment, and it can pick the.
Oh yeah, cool. But looks amazing. So where is it trained?
So let's come to the training part. So
Okay.
it is trained on the Intel Geti platform. So here you can see the Intel Geti UI, on which you can train your objects. So the first part which I shown you in the first part, the camera is connected. So camera is capturing the objects, and here we are annotating the objects. So here you can see. Here you can see that objects are trained, and after training, so you can select your model here.
So firstly, this tool is called Geti.
Geti.
Geti tool from,
So it is an Intel Geti
from
platform.
Intel, yeah. And this Geti is kind of a platform
Yeah.
to train such robots.
To-
Okay, cool. But let's go to the hardware. Let's know
Yeah, Max was here yesterday.
what kind of hardware.
So the hardware
the
is
train?
so we have the Siemens rack server. So these are called Siemens RW545A.
RW505.
5A. So these are the Xeon processor inside and having 16 to 32 cores, and you can use up to 830 watts power supply in this to enable the RTX GPUs from NVIDIA to train the models. And the model is trained on this Siemens hardware.
Okay.
There is another hardware from Siemens which is called Inference hardware.
From Siemens also?
Yeah,
Or
this is
from-
also from Siemens.
Okay.
So this is the this hardware name is called BX59A. It is a modular device on which you can stack more hardware in back to get the GPU power, or right now it is a base unit which is running only on the CPU. So the whole solution is running on the CPU at the moment.
And where is it?
This is the best design award also got from the Siemens. So this is the best hardware for experience and training at the moment.
Okay, so is the Intel chip is inside this?
And this the
unit?
inside it there is a Raptor Lake 13th generation Intel CPU.
Okay.
Yeah,
13th generation CPU from Intel.
from Intel. Yeah.
Oh yeah. Okay, cool. So maybe we can take a look back to the platform.
Yeah, we can look.
Okay, cool. And now we go to explain a little bit more about the platform. in order to configure just a robot. Hello,
Okay.
can you tell us a little bit about
Intel Geti.
Intel Geti? Yeah, of course.
Intel Geti is a training platform that makes it very easy to train vision-based inferencing models. You can easily create a new project. Here, let's call this new. You can define what type of algorithm, what type of task you want to do, segmentation, classification, anomaly detection, or you can even do chain task where you combine those algorithms one after another. For simplicity, let's take classification with one label that's already selected. You can say next, then you define your labels that you want to do.
So, for
Label
example,
one.
cube or so we can have.
We can
cube.
also cube. Can create it. Select the model. I can now annotate objects. There are tools to help annotation. So that uses the bounding box tool that already creates a bounding box and proposes one of the labels. I can accept this, of course. Yeah.
So now we are labeling kind of, yeah, with just one text.
Now we are labeling these objects. This is a twofold task. First, there is the object detection to detect that there is an object, and we do a classification to define what type of object it is. And as it is pre-trained, it already suggests a result. So this is a cube that's correctly labeled, and we can go on. And of course, we can also change this to say, yeah, to do this interactively. There is a tool to define or to help with the bounding box. This is its auto segmentation.
Wow.
I can simply click on it, and then you have a bounding box.
I can see even that it's included the shadow of the object. Yeah?
In this case, if this is not what you want, you can, of course, change it. And
Decrease its size or something, yeah.
change the size, and then set a new label. No, this is not what I want. Let's do this again. You can also select a new label.
Or delete the old one and then make a new one.
Let me delete everything. Try it again. Okay, so.
So the last slide that I'll show you for the demo is just to tell you what precision are. Robotics 365 is really built on 5 technology pillars.
Yeah.
Okay,
Let's
so
do it for now
we have
and
it like
do
this,
another
and then
Yeah. So
then the objects will be now labeled with whatever I decided to have it. So, for example, this is a cube.
So this is now a cube, object cube. I use the auto segmentation to have the perfect bounding box, and then set cube, so I can submit this.
So what we mean by that is to have application-ready components, which is the right, have the right hardware.
Use the next one. Okay, that's already correctly labeled,
Okay.
and go on until
And all of them, so it looks like we have 1,000
yeah.
pictures around. So, yeah. Okay, cool. And then after that,
And then I'm done. I can go to the model and train the model accordingly. Here for detection, I can also change the model to use. I will leave what we used before. So that's a YOLO X. And for classification, we used an efficient net. We can also change the models here.
Okay, so we have a model for detection and a model for classification.
In this case, yes, because we're using a chained model, a chained task here. So
Perfect. Okay.
then I can start the training process, and this runs in background. Once the training is done, I can deploy the model. So I have to select which model it is. So this was the chain model. I have a YOLO X. Can set the optimization here. Yeah. In this case, we leave it with FQ16.
Okay.
Then we have the second model, the classification. We can also change this, let's say this. And then we can download the created model, and it's available here in the download
Ah, yeah.
as a zip file.
A zip file. So now this zip file is simply a model with a labeled data, and then what am I going to be doing with this zip file in order to train then the robot here?
I download this zip file. Yeah, let's do it here as well. Let's do it here as well. I need to log in. So I can
And then finally software. And software, the idea here is taking the Renaissance tools like Script Studio and bringing them into the browser environment on the cloud platform so that the
It's very simple like that.
I can download this. I give it a version number.
6, for example, yeah.
Then I can select the device that I want to run it. Auto mode, GPU, CPU.
Okay.
And then I select Geti as the model source. I submit it, and then it's imported into the system.
Okay, so because the computer is connected to the GPU, yeah. Okay.
And with Intel Edge Insights system, I'm now able to use this newly downloaded model to create a new pipeline. To this end, I stop the old pipeline,
Okay.
and I just create an example pipeline for the new. So I give it a name. Let's call it test. I can select the camera source.
Because we have 2 cameras, yeah.
We have several cameras here. I add the model. So this is
and we were trying to do a plotter basically.
let me see which one it was.
Yeah, we 2 objects or 2 objects unknown, I think, or
Yeah, we
or
can
anything, yeah.
select the model
Okay, the model that we have already.
that we have downloaded. I think it was
Yeah, 2 objects plus unknown, yeah, one down,
so
exactly.
this one.
Exactly.
Then we select the a sync, and now we can simply connect those.
Okay, cool.
Tasks and create a new a new pipeline.
Yeah, I really like this graphical configuration, so you don't need to know programming in order to train such a
So no,
robot.
you don't need to do any program. You have a graphical editor to instantiate
Yeah.
it, and now in the scene, the model is running. And that's
Oh, now it's a real. Wow. So this is a real demo now.
so. Yeah, and it's running now.
And now it is running. Perfect.
So we can start the. The gun.
Okay, simple enough, just to train a model, and yeah, or to load a pre-trained model, and to configure the robot with whatever you want it to have. We have choose YOLO, but we can choose for detection, but we can choose other models, and we have labeled an object only to object, but I can label whatever I like.
Of course.
Perfect.
Yeah, so it is really a tool that helps you creating inference pipelines without needing to know the technology behind it. It's easy to use with a graphical editor. It's a microservice architecture that creates the pipeline with all security features enabled. You have databases that logs events, that provides metadata, and so forth.
Wonderful, amazing. So thank you so much for your time and all of this information. I hope I of course will write down in the description a little bit information about the tool, and maybe the people can get to know it, can get to use it. So I appreciate your time. Thank you.
Thank you very much.
Yeah, cool. So still in the Intel hoop. So let's see what we also can see here. So we find here some demo. So hi.
Hi.
Would it be okay if you can just take a little bit look of what you are doing, what
Of
you are
course.
offering?
No problem.
Great. So I can see here some apples. So I can imagine this apple would be detected by some model.
Yes, of course. So we can place these apples on this small conveyor belt and we are able to detect them, we are able to track them and finally count them when they cross the line, right? So this is a simple AI inference running here with OpenVeno and YOLO 11 model. And what's important, it's running locally on this small box only with Intel Core Ultra inside. So there is no connection to any cloud. There is no even discrete GPU card. Simple Intel Core CPU with integrated GPU and NPU.
I wonder if so the model is trained here in the...
The model was already pre-trained. We just converted it and optimized to run fast on this device.
YOLO
11, exactly.
It's pre-trained model. Okay, wonderful. And then looks like there is another tool to generate something. Is it related to this project?
It's related because of OpenVeno, of course, but it's running on this laptop here, so it's not the same device. And I think it's even more exciting because it's a visual Gen AI where we can prompt our model. Oh, I said our model. It's not our model, it's a model from internet. We just took it from Hugging Face. We just converted it also to OpenVeno and run on this laptop. And every 4 to 5 seconds we are able to generate a new image just running local inference. And once again, there is no cloud connection, there is no discrete GPU card, there is just simple Intel CPU, the same as is this small box.
Oh yeah, wonderful. So I simply can write whatever I want here in
Yes.
text, and then I can then see a picture.
Exactly, this should be a description of the image and then we can generate the image for you.
Okay, perfect. Can I try something crazy maybe?
Absolutely, yeah.
Okay.
Use this tablet for example and then you can type the prompt here. We are connected to the laptop, so we will run inference not on the tablet, we will run inference on the laptop there, but you will get the results quite fast, I think.
Okay, let's see. So now I have the tablet here, and I will be writing a YouTuber We'll try something as difficult as possible. Let me test the model.
The model is rather small, so probably it's not very capable to
So let's specify it with a camera.
capture a YouTuber, but no problem, let's try, let's experiment.
Is discussing technology. With an expert. So, let's see what's gonna happen. I just press the button, generate, and then
just 2-3 seconds
Wow.
and you have the result.
it's really very
Oh,
cool.
nice,
isn't it?
nice, it works.
Wow,
cool.
it works very good. Let me show it, emphasize it a little bit more. Oh, yeah. So this is now the result. Looks not bad. So I think I am this blonde guy, and who was hearing. But where is the camera? Yeah, but not bad. So I would like this to be printed for me. If it is
Yes,
okay.
we can do that. Of course, we have a sticker printer, so let me download it first and then I will print it for you. Okay, now it's printing, so
will
meanwhile,
take
I will tell you that we used also OpenVeno, which is a software solution for optimizing and deploying AI inference, so not only Intel hardware, but also Intel software to enable that hardware. And I am from OpenVeno team, that's why I'm here.
So, is it like a kind of an open source? So can I
Absolutely.
reuse it?
Everything you can see here is open source, so OpenVeno is open source toolkit for this AI inference, but also these demos here are open source. So this is a QR code here in the corner, and you can scan this, you can go to our GitHub, you can download on your computer and try running on your machine any of these demos.
Okay, cool. And now the picture is already done.
Oh yes, yes, let me stick it for you for this card, and then it's done.
Perfect.
Finally.
Good to go. Okay, great. Thank you so much for the information.
No
and
problem.
for the cards.
Thank you very much.
Thanks. So it's way to go. I have a very nice gift, and let's see what is also still to be watched here. Okay, wonderful. So this was a very great demo, and let's see what we can even still see here from Intel. But here, look, looks like there is here some application from the company Seco that built on the top of uses the microcontroller from Intel. Hello, hi. Would you like to tell us a little bit about this station? I can guess that it's charging station for the e-cars.
Yes, sure. So this is a joint project we made with our partner Linux Contact, and it runs on 3 different ecosystems. One is HMI, you can see here, the screen with all the hardware behind. One is the payment system, and the third one controlling the AI and all the power control is the system through this window. It's basically a smart module below the dissipator over there, based on Intel Amstel Lake, one of the latest processor.
You mean this upper white thing?
The upper one is the payment system.
Payment system, okay.
Okay, and then you see the dissipator, the green dissipator going out of the
Yeah,
board,
exactly.
of the
This is what I'm
of the
zooming in
carrier.
now. Yeah.
Below that, there is a smart module. Which
Yeah.
is basically is a little bit bigger than a credit card, the business card, and it runs on an Intel processor. And then there is also the carrier board, which is totally made by Seco.
By Seco, yeah.
Yeah, Seco is an Italian multinational based in Arezzo, which is close to Florence. We have 4 factories in Europe, 2 in Arezzo and 2 in Germany. And we
Nice.
produce everything.
Yeah, cool. So I am personally have already used the Seco model, but with with in XP, so
Yeah.
the version C26 is also pretty cool, handy to be used, and yeah, kind of straightforward to integrate.
Yeah. We work with all the CPU producers, NXP, Intel, Qualcomm, you name it, Rockchip, MediaTek.
Microchip, okay.
And also the latest one we introduced, we announced the cooperation is Raspberry Pi.
Raspberry Pi also. So I also make an interview with Raspberry Pi, so you guys would like to watch with it. And I am also happy that Raspberry Pi is breeding and you can also use it because there are a lot of variety of it. But back to this system. So yeah, okay, so it looks like there are 3 standalone systems and they are combined together to perform its task. But what kind of AI are played here?
On the carrier and on the smart module, it's installed the Clea system. Clea is our software suite that runs several different instances and is based and it uses the AI power. So basically the application here with the AI is the one you see here. It counts the people and it tells you if you are angry, happy, sad.
Look at me, I look very happy now. Yeah. And now when I like
one
when I'm happy.
face and one happy face.
Okay, awesome. And then it counts how many people are happy, angry, and so on, and give it a
I
feedback.
think so, but then it needs to be connected and the data needs to be extracted. But that is basically what Clea does. Clea does it with modules, even different methods products. So it's a very complete software.
Wonderful, amazing. Thank you so much for this information. And so let's go on to see what other applications that we can see. Yeah? So more and more applications on the MediaTek. I can find here a robot arm, which is simply shows some specific applications. So it makes simply some pictures of PCBs inside it, and it separated into different sections. So you can see here PCB1, PCB2, PCB3s. And as you see here in the picture, there is the there's AI algorithm that can detect what kind of PCB that comes from the camera. And everything is done, of course, here. So from the company Gren, they use the processor MediaTek, the Genius 700. So the camera is connected, and the robot is also connected via the Ethernet cable. And this is HDMI for the monitor, and the module YOLO is used here to detect the PCBs, exactly, and then classify them. So a trained model is loaded, and the classification is done offline on the processor. So again, this is one of more applications from the company MediaTek, and we can see here even more and more applications. So also for the camera. So don't wonder if Lugi is using a processor from MediaTek. There is even from Seco board, and new boards from Seco use also MediaTek S-Mark Genius 700 from Seco, which has a Wi-Fi in it. It has as an option if you wanted to use it, or TPM for security. Other application would be also the CYP company. Exactly. And So one of more applications here is also using the MediaTek to create some Android operating system from the company Kinetics. So again, more applications of embedded worlds. I can see here a very cool application. It's about the electronics of a motorcycle, of a scooter, whatever it is. So basically it's a Kaja FEI company. It's located in Japan, and they are using MediaTek and Yocto Linux distribution. So basically, in your helmet you wanted to speak with some other person, so you have a microphone connected to your helmet, or you wanted to go for navigation or something. So basically everything is connected actually from a mobile phone that is connected to the board by using a VLAN, and then you use the navigation system of your mobile phone, or even the microphone is connected to the mobile phone, and maybe somebody will say that there is some noise. So the noise will be reduced here by using AI. So these also should be integrated in the motorcycle. So yeah, a lot of applications. Yeah, wonderful. I like it.
A different application. So we are on the Raspberry Pi booth, and what we have here is the Revolution Pi. So first of all, when you want to create a new product or a new technology, you start with what you know and what you know is most capable, the Raspberry Pi. But then comes the time where you want to go into production, and meaning industrial production. And then you want something which is not an educational hardware, but a certified industrial hardware, which is rock solid and still pretty much the same as the normal Raspberry Pi. Meet Revolution Pi. Revolution Pi is a system where you can connect virtually any industrial field bus, any sensor type that is there in the industry, like even I/O link through external devices, but analog and digital, whatever you want. Still you are able to use USB for printers, for all the consumer hardware that you might like to add to industrial projects. For instance, cameras and industrial cameras also. What we have is enough compute module to run PLC applications in industrial real time, and in the same time watch videos on Netflix, for instance. So a big bunch of compute power. Of course, you don't want to watch Netflix. What you want to do is deploy your Docker containers. You want to go with TensorFlow applications. You want to go with number crunching like Fourier transformations. This is the great platform to create your own product based on an industrial grade hardware platform.
So here we have a small museum of Raspberry Pis. We have the Pi 1, the Pi 2, the Pi 3, the Pi 4 and the Pi 5. So this is all of our products over the last 12 years, our main SBC products. In a bit more detail, you can see a Pi 5 here. And what we've shown here is, let's get it the right way up. So this is our RP1 chip here, which you can see on the board there. This is the chip that provides all the GPIOs and a lot of peripheral interfaces for the Pi 5 to make it like a Pi. But let's have a look at some other products. Again, we've got another Pi 5 here, but this time with the active cooler on. As our product ranges have got faster and faster, the SoCs heat up more, so we need a bit of cooling on this one. This is an active cooler, turns on when it gets a bit hot, gets the system cooled down. So that's our SBC range. For the more industrial customer, this is our historical range of CM or compute module devices. Again, starting with the CM1, CM3, CM3 Plus. I think that's a CM3 Plus with larger eMMC and Wi-Fi. And at the bottom here we have our range of the new form factor, which is the CM4s here, a couple of CM4s, one with Wi-Fi, one there and one without. But this one here is our latest model of compute modules. That's the compute module 5. This is with the latest SoC, the same as the Pi 5, but again you can see the RP1 silicon there. What other things do we do? So we have,
besides that, there are plenty of, yeah.
so this is the Pi Zeros, both the 0 and I think on here a 03, 02 rather. So again, this is the sort of low end, the cheaper end of the market. These are very basic devices, very similar to the original Pi in performance until you get to the 02, which is more like a Pi 3. Some accessories to go on your Pis. We sell a lot of camera modules. This is various sorts of things. They're all described here. These are the camera module 3s, which are a basic 8 megapixel, or is it 12 megapixel camera. We also have a global shutter camera, which is good for moving objects, especially on production lines. And we have a HQ camera, which is a high resolution device. And over here, you can see an AI camera. Sorry, I smudged that, but this is the AI camera, the Sony IMX500. This has a built-in inferencing engine, which means you can use AI-style image recognition on our lower-end products like the Zero. And here we have a slightly older module, the camera module 2, which is still for sale, a slightly lower resolution module, fixed focus, unlike the camera module 3, which has an autofocus. And lastly...
It's the Pico.
The Pico, that's right. So this is the Pico 1. I'm afraid we haven't, we've misplaced our Pico 2 devices, but those who are familiar with the Raspberry Pi microcontroller, the RP2040, this is our range of sort of development boards for the RP2040. So we have these two here, one with Wi-Fi there, one without Wi-Fi, and these two are the same, but these have built-in headers. You can see that these already have the headers installed. And up here you can see this is our microcontroller, the RP2340, and this is what powers our Pico range. Unfortunately, I can't show you the Pico 2 because they're all over there.
Yeah, cool, but there is the applications of all of these museums we can see here, yeah?
Yeah,
okay,
so we can see here the AI camera that we described earlier. This is the Sony IMX500, and it's actually recognizing this as a Pi 5 with a fan on, which is absolutely right, so it's got that right.
Let's see, let's check. Oh, okay, the result is written here.
Yep, so right up the top there.
Okay, yeah, Pi 5, yeah.
With a fan, recognize the fan as well. So that's cool. Here we have the same IMX500. This time it's doing a person counting, seeing how many people there are in the image. It's seeing about 4 people at the moment. What's interesting about this is that it's streaming it via an Ethernet gadget to the Pi 5 here.
Yeah, but firstly, the model here is run on the camera itself, it's not in the Pi, yeah?
Yes, that's right. This is the IMX500, so the inferencing model is running on the camera itself. And the Pi 02 is simply taking the frame, converting it and sending it over the Ethernet, effectively acting as a streaming camera, a streaming AI camera. And that's all going into the Pi 5 here. This Pi 5 is actually driving both these displays. It's receiving the Ethernet, the streamed Ethernet imagery from this camera, but it's also capturing its own camera data and passing it through the Halo 8 accelerator here.
The Halo is now doing the
so this
AI
is
stuff.
Yeah, this is what's doing the AI stuff on this window. So it's recognizing so it's recognized me. I'm James. So it's recognized my face.
Now it's me, yeah.
So it shows how powerful the Pi 5 actually is in that it's streaming that data, it's driving both these displays, and it's running the Halo accelerator as well. That's a really quick run through of the products we have on the stand today.
I appreciate this. Thank you so much.
No problem.
Okay, cool. So looks like there is different applications now for Raspberry Pi. So what is it exactly about?
Yeah, this is basically the industrial Raspberry Pi, because the single board computer from Raspberry Pi is not actually meant for industry, but luckily Raspberry Pi invented the Raspberry Pi Compute module, which brings all the core technology of the Raspberry Pi. It makes it usable for industrial applications like ours, and so we built actually the industrial Raspberry Pi, which can interconnect with different I/O connections in industry, but also field bus protocols with existing PLCs. So you have an existing Siemens PLC, for example, you can hook up your Profinet, get all the data, and run applications like on a Raspberry Pi, but in industry with all software. You can run on Linux or Raspberry Pi OS.
Oh, yeah, cool. But when I program, I can program also the same as I am using very normal Raspberry Pi, Python and C++.
Yeah, you can use the same programming languages. You can use, for example, C, Python, and other languages. You can use a low-code approach with Node-RED, for example. So you don't need to program, you just make some flows. But also, if you're interested or coming from an industrial background, you might want to check out Codices and use all the industrial programming languages on the Raspberry Pi as well.
Oh, yeah. Wonderful. Great. Thank you so much.
Thank you.
So this is the car cockpit. You can see here the camera from the company Microchip. Super lightning.
So what we're showing here is our FPGA-based face recognition demo to do like a car entry system based on a face which is getting trained in the model. So the FPGA is running our vector block solution, and if you have the right image, you can actually unlock the car. So here we do the demo. So this is a trained face, so you see the car is opening.
Oh yeah, wait. Oh yeah, okay, so here the car is open, yeah. Because the face is recognized by the camera.
Exactly. So the camera is going HDMI to our FPGA, and there we have our vector blocks AI solution running, doing the face recognition.
Yeah. And in the background, so it's running a PolarFire system,
Exactly. It's
system on chip.
our PolarFire SOC Video Kit.
Okay, and it is connected of like FPGA and processor itself.
Exactly. You have a processor portion and you have an FPGA portion, but the FPGA side is doing all the AI processing bits.
Okay, so the model is saved inside the FPGA.
Exactly, and calculated as well. So it's doing the inferring bit of the calculation.
And is it trained inside the FPGA, the model, or it is like trained somewhere else?
The model is trained outside. So you come with a trained model, and we have a vector block solution to convert it into the FPGA design.
Ah, okay, this is pretty cool. So this is like one application of the PolarFire.
Right. It could also do like object recognition or license plate detection for like a car entry system in a parking garage or something.
Oh, yeah.
Or some driver distraction algorithms. So there are plenty of
But of course, in the future, like unlocking the door of my car with just a camera, I don't think it is something very practical.
Yeah, it's like the unsafest car door in the world.
Okay, but there could be some other credentials that
right. So
can
in a real
detect
application, you would have a 3D camera to do a detection if there's a real human in front of the car.
Oh yeah. Perfect. Awesome. Yeah, I appreciate that. So this is a door of the future. Thank you so much for the information.
Thank you for coming by.
Okay, cool. So more to the iSkill kits.
SOC Video Kits.
Oh, nice. SOC Video Kit. So this is kind of an application case. Can you please tell us a little bit about this application? What is it about?
Yeah, so this is our PolarFire SOC time-sensitive network, or TSN demo. So what this is showing is the benefit of TSN, or the real reason why you'd want to use it. Because, for example, here we have TSN enabled on our device, so that gives us the TSN support. And if I click flood traffic here, so what that does is generates a ton of networking traffic. And with the TSN enabled, you can see the motor spinning down here on the left-hand side. And that just means that basically we have our time-sensitive networking to make sure that everything works properly. But if I disable I'll leave that on. If I disable our TSN support, the motor is actually going to stop spinning in a second because the network is overwhelmed. So it's spent so much time dealing with all that traffic, it's not functioning anymore. So the TSN allows us to make sure that our time-sensitive tasks are always running and keeps working for us. So if I re-enable the TSN, the motor starts spinning again for us.
Okay, cool. And so who controls the motor actually? Is it the fabric FPGA or the processor?
So what we've done is, this is PolarFire SOC. So in there we have a 5-core RISC-V processor subsystem, so 1 monitor core and 4 application cores. And it's actually running Linux at the moment. So Linux is running and providing us, for example, this nice UI that we have shown up on the screen on the web server. And then in the FPGA fabric, we've implemented the time-sensitive networking IP. So the SoC, the processor side, is controlling everything, but it's using the FPGA fabric to add the functionality for the TSN. So we've PWM, for example, going to the motor driver to get it to spin at the rate that we'd like.
Oh, so this is the motor driver, yeah?
Yeah, exactly.
Mm-hmm. So the motors, is stepper motor, I think?
Yeah, that's the one.
It's connected to this.
So that's a stepper 7 click. So from Microelectronica, you can find it up on there.
Mm-hmm. And then all the information lands here in the processor.
So this is the main part of our device. So it's the PolarFire SOC FPGA. So the processor subsystem is interfaced up via the FPGA fabric to our FMC card here with one of our Microchip PHYs. And then our PWM is also interfaced to the FPGA fabric to drive the motor. But the main thing is the PolarFire SOC FPGA, and it's really nice because it's a really low power and high performance FPGA. In terms of the temperature, it's nice and cool, but it doesn't need a heatsink.
Okay.
And you can actually put your hand on it, it doesn't feel hot.
Yeah, not bad.
So you can avoid having a heatsink or a fan. So for a thermally constrained environment, it's really, really beneficial.
Mm-hmm. Okay, cool. And so basically the PWM is controlled by the processor.
By the processor subsystem, yeah. So the Linux operating system is running, doing the web server, doing the PWM control, doing the TSN, all of that stuff. Because we have 4 application cores to use from, so we have a ton of bandwidth there to be able to do all of the processing that we require.
Yeah, so you can even run a server, I think.
Yeah.
Okay.
Yeah. Anything you can do on Linux, you can do on PolarFire SOC.
Oh yeah, perfect. Great. Thanks. Okay, cool. So this was an a kit.
This is the PolarFire SOC Video Kit. Yeah.
Video kit. So you can also connect a camera to it.
Exactly.
And, yeah. Okay. And more about connected cameras. I see also here a real camera is connected to other kit.
Yes.
From PolarFire also.
So this is a partnership we have with NVIDIA. So this is our NVIDIA Sensor Bridge demo. So what this is showing is we have a camera here with the MIPI interface, and the PolarFire is basically used as a sensor bridge. So it's bridging the MIPI interface to Ethernet and sending the data to the NVIDIA Orion over Ethernet.
Oh wow, okay. So the NVIDIA is connected to the board via Ether cable to the processor. So it's also processor and fabric together?
No, this one's just a plain fabric. There's no processing involved.
Only FPGA, okay.
Yeah, so it's just being used as a protocol converter. It's MIPI to Ethernet. So it's giving you that really nice bridge. But it means you're a lot more flexible in what cameras you can use and what you're doing.
And the camera is connected to the fabric?
Yep.
And then we can detect objects here.
So what this is running, this is using the NVIDIA Orion as the actual AI engine. So there's no inferencing or anything like that happening on the FPGA itself. It's just doing the MIPI to Ethernet conversion, and then all of the AI side of the house is being done by NVIDIA. So you can see it's drawing the box or the shapes on us to show what pose we have, but that's not being done on the PolarFire FPGA. We're giving you that bridge. So
okay, and how is the connection now? So the connection between the NVIDIA board. So firstly, do you know which board it is for NVIDIA? Is it Nano?
No, this is the NVIDIA Orion, as far as I remember.
Yeah, it's okay. So any of the Jetson NVIDIA, I think, could be the same. And this is it really simple, like via an Ether cable? I can be running the application from NVIDIA?
Yeah, and then it's just plug in and play. So it means then you have much more flexibility in terms of cameras. The interface into the NVIDIA board is always Ethernet.
Yeah.
And then the camera conversion is done by PolarFire itself.
Yeah, good. But what would make me to do this if I can connect the camera directly to the NVIDIA? Is it like I can connect more sensors to the board, to the Microchip
You can
board?
connect more sensors, different cameras, different types of interfaces. So at the moment this is showing MIPI, but you can go with different protocols as well. We're adding more and more support over time. So it gives you a lot more flexibility. So with the combination of the two boards, then you can go with a whole array of cameras. You're not limited to what you want to do.
And can I also like load the data from the NVIDIA to the fabric and reprocess it in the fabric? Kind of like the same is done in the system on chip?
In the SoC video kit. So in this case, no, the fabric is just being used as the protocol converter. If you wanted to do something like that with the SoC video kit, we do have a camera connector here for the Sony IMX camera. I can't remember the name, the exact one off the top of my head. But what we can do here is the cameras interface into the FPGA fabric. And we have some DDR for Linux to run and DDR connected to the fabric as well.
The DDR is the memory.
Exactly, so we can use it to store the video frames.
Okay.
But what we can put in the fabric here is a neural engine, so we call it vector blocks as our one. And we can use that to do object recognition and inferencing, for example, and run a whole load of different or whatever algorithms you would like to run. So if you wanted to detect faces, if you wanted to detect objects, if you wanted to process the data in some way, you can do that. And then you can get the process data and give it back to the processor subsystem.
Okay, cool. And can we see other applications from PolarFire over there?
At the moment, the two demos we have today, we have PolarFire SOC here with our TSN networking, and that's the one that also can do the video processing. And PolarFire here is our sensor bridge with NVIDIA.
Okay.
We have a ton of really cool demos. One of the great ones we have over here is PIC64. That's the Curiosity kit running a web server and a MIPI to HDMI bridge as well, which is our entry into the 64-bit NPU market. So it's a really cool demo, actually.
Okay, can we see it?
Yeah, come on along. That's right. So here we have the PIC64 Curiosity kit. So what this has is we have our camera connected up with a really interesting fisheye lens.
Oh yeah.
And what this is doing is MIPI to HDMI conversion, but we're running Linux on this. So we have, again, 5 cores, so 1 monitor core and 4 application cores. So while the sensor,
So sorry, before you explain this course, so again, this is not PolarFire.
No, this isn't PolarFire SOC. This is our 64-bit NPU.
64-bit NPU. Okay.
Yes. So this is similar-ish to PolarFire SOC. It's RISC-V based. So we have 4 cores available for Linux.
Okay.
And Linux is managing this video output here through our MIPI to HDMI pipeline. But this is actually picture-in-picture. This is the HDMI input to this screen. So this isn't streamed video. This is the sensor bridge running, but then up here you can see we have our 4 cores, our memory amount, or the amount of system RAM there, so we're not actually using a ton of system resources to run the video pipeline.
Yeah.
And then in the background, we can play Space Invaders if we want to,
Wow.
which is quite fun. And we can also, on the right, we have a web server running in Python. So it's just to show
So 1, 2, 3, 4 different applications
simultaneously.
Simultaneously, that's
without
cool.
breaking a sweat. Now I think our network might have slowed down here, unfortunately, but if I go up, I can reconnect and get HTOP to restart. There we go. So you can see the CPUs aren't actually breaking a sweat. I have the ASCII invaders running in the bottom down here, so that's quite nice. I can play that. The video pipeline running, the web server running, and we're not breaking a sweat with the CPU utilization at all.
Oh, wow. Okay, cool. But could be any kind of an application to connect or to change, to communicate data from one core to the other? So not like separately, but in parallel, but they do something to.
So a good example of that is ANP, or asymmetric multiprocessing. I think that's what you're getting at. So with our 4 cores, we don't have to use them all for Linux. We can take 1 core away and use it for a real-time task, like running an ORTOS like Zephyr. So in that case, if you think of something like a robotic arm, where you might have a real-time safety-critical task, like stopping the arm at some point, you can get Zephyr to do your real-time operations. Whereas in Linux, things might get scheduled, there might be a delay in something happening, but if you have an emergency and you want to stop the arm, having the real-time operating system running beside Linux, all on the same device, in the same package with no delay, allows Zephyr to do the safety critical stuff and Linux to do the heavy lifting like running a web server. And then those two contexts can actually talk to each other. So Zephyr could tell Linux, by the way, I stopped the robot arm. You don't need to do anything but maybe display a message. But the safety critical stuff has already happened without any kind of overhead of the OS trying to schedule a task or waiting for something to happen.
Wonderful. Very cool applications here.
It's
very
really
cool user
fun.
case. So I appreciate all of this information. Thank you so much.
Cool. So it's really cool.
Hello, here we have TI's medical demo enabling Edge AI on ECG applications. So typically when you think about running AI algorithms on ECG platforms, you might see something where you'll capture all your Bluetooth data and send it to the cloud. And then 2 weeks later, a doctor might take a look at it and tell you that you had a heart attack 2 weeks ago, which is not great. So what we actually want to do is enable you to do detection almost instantly with very low latency. So if I switch over to a severe heart rhythm, you will actually see that after a short time of buffering, we'll get our emergency rhythm or our severe rhythm coming in here. And then as soon as it hits over here, the AI detects it and we mark a severe rhythm.
So how did you, from where does this signal come from?
So the way that this demo is set up.
Should come from here, or?
Yes. So we actually have, so this is our interface device that is generating the signal. We have a signal generator inside of the mannequin, and we have our Texas Instruments analog front end. So the really good advantage about going with TI is that you actually have analog, embedded, and power capabilities. Within our device, we're using our TI buck and boost converters. We're also using TI's analog front end. And then if I open this up, you will see TI's processor with the TI BLE chip. So this is actually the device that is running the AI hardware acceleration algorithm. So because it has an AI hardware accelerator, you can achieve much lower power than a typical implementation with CPU in a software AI implementation.
Okay, cool. So this is basically what is inside this here.
Yes, and so you can see that right in here.
Okay. Perfect. Ah, yeah, okay. With 2 batteries to get the power.
Yes, and that's for the power. So that signal generator that's on the inside is actually outputting the signal through these electrodes. These electrodes get fed into our analog front end, and then that signal is sent over to the processor in the AI model.
Okay, cool, yeah. And now the result of this guy is actually that it has...
And the result is being transmitted via Bluetooth low energy over here.
Okay, yeah.
And so if you take a look and I switch over to normal sinus rhythm, it's going to take a little while for the buffering delay, and then you can see the normal sinus rhythm coming in. So what's one of the other big advantages here is that with the lower channel count, you can actually vary how many channels you have active at the time. So whenever the patient isn't experiencing any type of cardiac issues, you actually have all the other channels turned off.
So what, can you please tell me a little bit, what is this?
Yes.
These channels?
So there's 4 ECG channels being sampled on the device. This is why we have 6 leads. So you can take the potential across the heart here, across here, across here, across here, for example. You have 4 different channels. However, you know, during typical normal applications, you don't need to be running all 4 channels. Only 1 channel is sufficient. Whoa. Let me click on that one.
So is it kind of a redundancies to have exactly the same data?
So once we reach a severe rhythm or an emergency rhythm, what we want to do is start sampling so that we know, okay, what's going on with the heart? Is it a particular spot that's not working well, or is it another one? So by engaging all the different channels whenever it detects a severe rhythm, you can actually see on multiple channels, you can see how the heart is basically operating.
Okay. Cool.
And what the ECG is being detected. And so this kind of variability lets you get lower power whenever nothing's being detected, which is the majority of the time, you're running at a lower channel count for lower power. As soon as something is detected, then you can up the power for a short time and really run it faster, get more information. And this can help your AI classification as well.
So what is the result now of this guy? So is he in a good condition or what?
So now it's a severe rhythm. Condition is not good. The mannequin is not happy.
Oh yeah, that's very sad. So we have to get him to the hospital.
Yeah, we can't see the face, but he's sad.
Okay, cool, yeah. So I appreciate all of this information. Thank you so much.
Yeah.
Right. Perfect. So talking about how an easier approach to program Texas Instrument microcontroller C2000.
Yeah, that's exactly it. So basically, I'm from MathWorks. My name is Antonin, and today I'm showing a demonstration on how to simulate the behavior of a controller on Simulink, where you can program a DC to DC buck converter. This is what I'm showing here. So you have a C2000 controller, which is controlling a DC to DC buck converter, and this is provided by TI. And we have a Simulink model that helps you simulate the behavior of the plant so you can create your controller algorithm without writing any line of C code. And here, once I'm happy with the simulation of the controller, I can press one button, generate code for the controller, compile it, and load it on the board so it executes immediately. Once the code is loaded on the board, I can visualize what's happening in real time. So I have a host model that I can run, which gives me the results of my controller and helps me monitor signals. So here, if I launch it, basically I can see voltages, and I can turn on some load, which gives me more, some disturbance in my algorithm. I can remove load, and I can see how good my DC to DC buck converter is behaving.
Okay, cool. So this specific DC-DC, how is it simulated now in MATLAB Simulink? So do I have to write everything from scratch, or is it a block or a module that I can simply load it?
Yeah, so we have a series of blocks that support the C2000 family of processors. So we have blocks to access ADC, PWM, serial, I2C, SPI, you name it. Pretty much all the peripherals of the C2000 controllers are provided. When we generate code, we create a real-time scheduler. There's no OS, it's purely bare metal. Actually, the demo I'm showing today runs at 200 kilohertz or 5 microseconds. That's the time we have to run the control loop. So it's very fast, bare metal, and we try to have the lowest latency as possible.
But am I limited with this DC-DC, or can I use other DC-DCs?
No, so you can program whatever you want. Here I have a DC to DC buck converter. I also have a motor control demo based on the new F29 processor that TI just released. But yeah, the application it's a programming tool. You can pretty much program whatever you want. There's no limit to any type of algorithm. Though we have tools. For instance, we have a motor control block set that provides a lot of bricks to help you with motor control. To detect parameters, do your field-oriented control, and your position decoder. I mean, there's a bunch of things provided with this.
Okay, so after you kind of simulate the physical world into MATLAB Simulink, and then you add your program, your control part, whatever you wanted to do with this physical world, then you generate a C code.
That's
that will
correct.
be running in the microcontroller.
Exactly, yeah. We generate C code that we compile with the TI tools. We integrate the C code with the drivers provided with the blocks, and we create the scheduling glue that's around it. So we schedule tasks based on interrupts, based on timers, based on idle tasks. You can configure that from the Simulink model.
Okay, cool. So how about like this here? Is it other?
I think Johnson would be the best to describe this. This is a different solution created from TI to program the MSP M0 family of processors, which is a little different.
But can you also program the?
Not with Simulink.
Not with Simulink anymore. Okay.
Simulink focuses on the C2000 family of processors.
Okay, yeah, perfect. Amazing. Yeah, thank you. Okay, cool.
Okay.
And then there is another way also to program the microcontroller C. What is it called? The microcontroller here? What is it? Do you know its name?
MSP M0. Actually, this is MSP M0 G3507. This is G series.
MS0.
MSP M0.
MSP M0. This is the microcontroller.
Yes, correct.
Okay, and there should be instead of programming everything from scratch, we can then use the MSP Zero Code Studio. Okay, so would you like to tell us a little bit about how to use it, or if there is a small demo about it? Can you tell us about it?
Okay, it's fine. And actually, you can find we will have a tools. This is the MSP Zero Code Studio, and actually we already prepared some demo here. If we open a simple demo, you can find in the left side, we will have a lot of modules. You can find some delay, some update demos, some GPL writer module, LED module, and a lot of modules here. And then, if you want to implement any function, you just select this one, and add the module is fine. Just like I will add the LED toggle module here. And I will choose this GPL is PB26, and we can also change this GPL file. This one, and then we can also add other module, just like we add the delay module. This one, and we can set the delay time maybe the 1 second, and just connect the wire is fine. Connect this one, connect the delay module for the LED toggle, connect the LED toggle for the end point, and then just build and load is fine. Maybe we need some time to loading.
Okay, so basically you have made here one delay.
Yes, one delay and the LED will toggle.
And an LED. Okay,
yes.
one of these LEDs that are here. Yeah.
This is LED.
Actually, this LED here, the yellow one.
This LED, yellow one. Yeah.
Okay,
correct.
yeah. But you have access to the whole 6 LEDs.
Yes. This is LED.
And now, after you flash it, you can now see that it has 1 second delay.
Yes, 1 second toggle. On off, on off. This is a very simple demo here. And actually, we support a lot of modules, just like the PWM, like the others. That's if you see our module control advanced version demo. This is more complex because we already made some module in advance here.
Okay.
You can find we can change some PWM duty. This one. This is the left motor, this is the right motor. And we will change some duty from the 25 to the 60. And you can find this motor spin speed will be changed. And I can also build this demo and down and loading.
Now you are controlling the PWM of the motor.
Yes.
Of these
we have
motors.
2 motors, left side, right side. Okay.
And then now you convert now your graphical coding into a C code, or?
Yes. You can
look
find
at it, yeah.
This demo function is shown here. The left motor and right level. We will have some logic here. And any logic will use our Zero Code Studio, no any coding. And actually, we will also generate the source code here. You can find any source code here.
Okay, you can even modify the source codes.
Yes, correct.
Okay, the C code. Is it readable? Because usually developers have problem with generated code.
Yes,
to read it.
This is C code.
Okay.
You can copy and change anything. Yeah.
Oh yeah, cool. But how about if I have now if I wanted to connect a third motor. So is it like kind of flexible to perform such a thing?
Yeah, actually, if you want to control the third model, actually just add another PWM is fine. Actually, you can find we only add 2 PWM anti-spy here.
Okay.
You can add another one is fine because actually M0 they will have a lot of resources here. You can find this is our landing page. M0 is a 40 megahertz CPU you can find, and if you saw our block diagrammer, a lot of resources here. Actually, you'll find a lot of resources here. Just like if you
so this is the GPIOs and
yes,
whatever.
GPIO is for LED control. Timer is for motor control.
Okay.
You can find we only use the time A0 for those 2 motors. Actually, every time A0 can control 4 motors.
Mm-hmm. Yeah, cool. And then you have full control of your board without any
yes
limitation. And so the MSP Zero Code Studio, is it limited only for such a microcontroller, or you can use it also with other microcontrollers from Texas Instruments, of course?
Actually, this is designed for MSP M0 platform.
Only these microcontroller?
Yes.
Okay, yeah, perfect. Cool, yeah, I appreciate this information, thanks.
Okay.
Welcome to our booth. We are System Electronics, and we are happy to introduce Atrial. Atrial is a set of modules that we designed based on IMX8 Plus and ILO chips. These modules are meant for edge computing, for industrial application, when you need extremely high performance, low power consumption, and compact solution in a CM form factor compatible. What does it mean? This means that you can plug this board directly into Raspberry Pi carriers due to the CM4 or CM5 form factor compatibility. Okay? So, this is Atrial, our module based on IMX8 and HILO 8, built with industrial grade components for any kind of application, while this second module, called Atrial H15, is based on ALO 15 chip. It's a ISP integrated chip where you have the wire vision pipeline embedded into the product. So you just plug the camera into the module, and you have AI performance and CPU to run your application.
And how to connect the camera?
This is a CM5 module, so you can plug this module to any kind of carrier, both commercial or custom carrier, enabling you to rapidly get into the product. Okay? So here in our booth, we have 2 demos. So follow me for the first one, where we show a full customized solution. So we have our module in a vision system, completely designed by System Electronics, where we integrate the camera, the lighting system, and the compute module into industrial grade hardware to perform, for example, hand detection. So as you can see in the video, this application detects the pose of the hand, recognizing if the hand is open or closed. The system is able to process multiple streams, like in this case. Roberto, can you help me with your hands?
Yeah, sure.
You can see that the system is able to recognize multiple streams of video in real time. And this is perfect for industrial application when you need to handle with the logistics, with operation, and activity where people behaves with machines. We have another demos about avionics. Where we showcase an application with the drones. So we have, as an example, we have a drone with a Holy Bro flight controller, where we plugged our module, and runs directly thanks to its CM4 compatibility. So this demo is running on an avionic platform, allowing with almost zero time to market to test your application, to test your software, and run a real product. As you can see here, where we do people detection and face recognition.
Okay, wonderful. So, as a beginner, for example, if I wanted to make such a drone, so how can I get myself started? So, what kind of processor should I order from internet, and what other components should I have it?
Okay, now I let the stage to Roberto to face this topic.
Yeah, sure. You can start from downloading the full image from our GitHub. It's completely open source. It's based on Yocto, so it's a full Linux image where you can start from scratch all your development, and you can find there the API to communicate with the Halo. So you can find also the example here that you can find here in the demo, and you can also communicate with the flight controller as well. So that has its own API, of course. Yeah, so basically it's pretty straightforward. You just need to power it up. And
only the motivation. So
yeah.
basically, for the hardware, we need from the processor. Where is the processor?
Yeah, I guess someone installed it. Yeah, this one.
But actually, you need this processor.
Yeah.
And then run AI
directly on the edge, so directly on the drone. So yeah, and you can also handle at least two cameras if you want.
Connect two cameras inside it.
Yeah, exactly.
Okay. And then this microcontroller, it will send commands to
the flight controller.
To the flight controller.
Yeah.
Just to connect, to control the motors.
Yeah, exactly.
And then we can then run any kind of algorithm to detect if there is something in the...
Yeah, the imagination is the limit now.
Yeah, autonomous driving is one of the most, obstacle avoidance, and detecting also object or counting items like vehicle in a car parking or detecting the license plates. So those are the use cases. But the same models can be used also in mobile robotics, so indoor navigation when you don't have GPS, so you need to rely only on sensors or cameras. So this is a very increasing market. So Atrial is meant for performing this kind of task. When you rely on sensors, on cameras, or you need to perform navigation, using the lowest amount of energy, power, and resources as possible.
Wonderful. So I think I am starting now to think of being a customer of you by trying such a drone. So let's see. And I appreciate that you have it open source, the code. So this gives me the motivation to try it out.
Yeah.
Thank you so much for the information.
Thank you. Visit astrial.ai for further information.
And of course, I would write in the description below the contact to the company, and if somebody has a question, people are very helpful. So don't hesitate to get in contact.
Thank you.
Thank you.
Bye.
Bye.
Oh, this is the EMX93, I think. And then here STM, other application. Ah, right, yeah. I know this is the most difficult program ever you would ever program. Yeah, this is very tough.
Yeah, it's a hardcore calculation.
Yeah, exactly.
It's like a hardware floating point unit
Yeah.
on board, and it's like really accelerating the whole stuff.
Wow.
Like you get if you do single precision, you get like almost 70 times of processing power. So quite amazing.
Oh yeah, cool. And this is from the chip, microchip, or?
Yes, exactly. Microchip board, and it's like kind of a dev board or eval board. So you see here the DSPIC 33A plugged in, and then like some micro E boards over there, which are used for showing the demo. So for example, this one is especially showing the FPU processing power, and there's another one because it's especially good in analog digital conversion. So it has like a 40 megasamples ADC on it, and so we have like wave generation with like 85 megasamples, and we put 1 megahertz on the thing, and we have like a really nice sampling user interface. So we can see like the waveforms coming out of the wave generation, sampled by the ADC on the DSPIC 33A, and yeah, with a really high resolution, I would say. We will also have like several waveforms, so you see like a triangle. Yeah, this is actually a triangle. The sign is as well there. So this one is the sign with RC filtered actually. And yeah, you could set a trigger here, for example. As well, like putting the trigger up, so you see the waveform running, or you like, properly trigger it. You can like also like zoom in and out, and in the moment you see like this is the reach frequency of the wave generation, so approximately a megahertz. And,
so this is a signal generator.
Actually, it's more for recording the generated signals, but it has like a extension on the board for micro E boards, and we have a small board on it with a wave generation, and this one is then sending it to the ADC. Exactly.
So I can imagine this could be, for example, used in oscilloscopes.
Yeah, sure. For example, yeah, exactly. Yeah, I mean, like not a high-end oscilloscope, but for sure, like something that Digilin, for example, is doing, like for student purpose, prototyping, and so on. So yeah, quite nice. And as well, like doing a lot of calculations on the.
Oh yeah, this is the matrix that's here to make these calculations.
Exactly. Yeah, to make especially like it's a kind of a moving donut.
Yeah.
And yeah, I mean, you see a lot of cosines and sines in it, so it's actually really hard to calculate and.
It needs a very good hardware, yeah.
Yes.
Great, yeah. Thank you so much.
Thank you.
So hi, yes.
Hello,
so we've
hi.
got the in-hand IAI edge computers, starting from our lower end devices, progressing up. And the progressing up is the performance of each device is improved. So as you can see, we start with 1 TOPS, and the top is tera operations per second.
Okay.
So as you can see, it increases up to 100 TOPS applications. So these type of applications would be like our simulation there.
Okay, great. But this is It's 100 tera
operations per second.
It's pretty. I mean,
Yes.
it's like, is it more than Nvidia? I think.
Actually, it's got NVIDIA processors inside it. So
Okay,
that's yes, that's the power.
So you
of
are
this.
building kind of a system.
Yes, this is a whole system, and also it's a 5G, 4G router as well. So it's it's full connectivity as well as an edge computer device. It has full 4G and 5G connectivity.
Okay, and here you can connect some monitors to it.
Yes, these are for basically allows us to connect to other devices as well. So you've got USB devices, Ethernet ports, HDMI devices, and these are the old COM ports that legacy devices use, sort of thing. So, and then there's dual SIM cards in there and other digital input. So yeah, you can put multiple SIM cards.
Yeah. Okay. Maybe we can show it to the camera also. So like there is an opportunity to put from here a SIM card to save some data.
Yes, provide 4G and 5G connectivity. You need SIM cards to provide the connectivity.
Okay. Also the USB.
USBs and antennas both for 4G and for Wi-Fi as well.
Yeah, wonderful. So this is starting from
A single top all the way up to 100 tops, so we can be flexible in the configuration that we can provide our customers based on their computing needs.
Wonderful. And looks like there is a great demo here. Of
Yes, so there's a live demo here.
So first of all, which system are we using?
That's the EC550.
EC550.
5550.
Great.
And on this demonstration here, we're showing a edge computing with a application that is built by in-hand, just showing a driver's awareness assistant. So if I'm a good driver, I will be driving with my hands on the wheel. If I pick up a cup of coffee or something, it will warn me that I'm drinking.
Yeah.
Therefore, this could be used by an insurance company to incentivize people not to drive irresponsibly. And I could also sunglasses as well. It could warn me if I'm wearing sunglasses as well.
Yeah, sunglasses.
Yeah.
So it could be by insurance company.
It could be insurance companies.
It could be as well also by car manufacturers.
Car
to make
manufacturers
some signals.
as well.
Hey,
Yes. Yep.
You're
definitely.
not allowed to do this
Yep.
or something. Wonderful application. And I think it's also very great that everything is running locally without connecting to the internet.
Yes, but it can be connected to the internet. So, you know, you could be sending data back up to your cloud platform, and that could be monitoring the individual as well.
Okay, great. And this is the camera that...
yes, this is just a camera showing the pictures.
And maybe this camera, can you take here, the connection? Via an ETA cable here. Wonderful, yeah. So, software. So, in the software sides, can we take a short look, or can we discuss a little bit?
So,
how
the software is
it?
produced in hand just for this demonstration purposes. So, we are a hardware manufacturer. We're just showing an application, but it will be our customers' applications will be placed on this.
Okay.
So, we're not really a software company. We're a hardware company. We can support companies in making sure the hardware supports the software. Okay.
I understand. So basically, the companies, your customers, they will be dealing with NVIDIA boards. So one of NVIDIA's, in order
so
to
the NVIDIA is
their...
based already in this platform, but they will be using the operating system and placing their application there to run on the device.
On NVIDIA,
Yeah.
kind of. Okay,
Yeah.
great.
In this
Wonderful.
particular situation, yeah.
So great application. Thank you so much for all of this information. And I will pay a visit, of course, to your homepage. I encourage also everybody to do this. And yeah, get in contact if there is any interest or any question.
Thank you.
Thanks.
Thank you.
Yeah, cool. So there is also another, again, applications from system on modules that looks like can be used for fitness.
Yeah.
So would you mind if I tried it out firstly?
Yeah, go ahead.
Okay. So I will just hold. I think it's 5 kilos, yeah. Maybe you can explain what is happening here?
Yeah, so currently the machine is providing you with a resistance that is equal to 5 kilos without simulating any inertia. You can have the machine instead simulate an actual weight. So now it's going to simulate a 5 kilo mass that you have to put energy into. But it will also be a mass that will move by itself.
Yeah.
And then of course we can do mixes of these where you have to put energy into the system, but you don't get the free ride that you would generally get with a dumbbell.
Okay, interesting. And what kind of electronics is used here?
So we have two systems in this machine. We have a microcontroller half, that's the motor driver, and that's built with code from Simulink in MATLAB. And that reads, so we send it what load we want. Internally it will be converted into a torque. The torque will be converted into, via motor configuration parameters, a specific current. The current will be, then we will calculate from the current the voltage we need for the current, and then we will do a duty cycle based on the voltage that we need.
Okay, so that's like the voltage is converted into kind of a weight. So the voltage is converted into kind of a weight, because I don't think that this machine has weight inside it.
Yeah, so you are feeling the resistance of an electric motor. So when you are pulling the line out, the motor will act like a really strong generator, and we modulate what we ask it to do to give you the torque that you requested. And when instead the line is returning into the machine, it's a basic electric motor. It's a 3-phased electric motor.
Oh yeah, cool. Okay, cool. So more about the electronics in the what is inside these black box?
So yeah, other than the microcontroller, we have the computer board. The brains behind it is one of these Toradex modules. So you get a module that is a complete computer, but without any actual ports. So you have an edge connector, you need to expand them somehow, and that is, in this terminology, a carrier board. So you connect your module to the carrier board, and then you have the actual ports you need. And that is, for instance, how we connect the display to the computer.
So basically it's exactly the same system or module that is used here?
Yes, so we have the exact same module that they've used here, but the carrier board that the module is attached to, we have our own custom one.
It's something else because it has to be connected with the...
So here is where the computer is.
So this proves that there are a lot of applications for electronics and electricity. So it can be also used in fitness. Yeah. So I appreciate the information. Thank you so much about it.
You're welcome.
Oh yeah, cool. Okay. Looks like it was trying to jump, but it can't. So now you are rebooting it by somehow.
Yes. So I'm rebooting it, and you're gonna see that the M4 core comes up much faster than the Linux, right? So now it tries to balance itself, and then you're going to see on the screen that Linux is going to come up, but it's already balancing because this is running from the M4 real-time core, and the GUI is actually running from Linux using the Crank framework.
Oh, okay, so there are two different processors here.
Yes,
and what
exactly.
is this? What is here? This application?
So it's an IMX8M+, but the real-time processor, the processor itself, the real-time core, actually is inside the SoC itself, right? So you have a single package with the application core, and you have the M core on the same package.
Okay, yeah. So it shows usually a smiley face, or what?
Yes, it shows a little smiley face, and it also has a game because the screen is actually a touch screen. So first of all, you can actually,
push it. Oh,
yeah, it gets angry. But we can also tap it, and then if the lighting permits, whoops, trying to find the lighting. Yeah, this one cannot find the neural network because of the lighting probably, but this one. So if I press, it's gonna say 3, 2, 1. And it actually plays tic-tac-toe.
Oh wow!
Yeah, so it was supposed to win, but because I actually lost. But the lighting is making the camera a little bit not work so well.
But is just, can I place these cameras as well?
Yeah, you basically just have to lightly tap it.
Okay, can you tap?
So lightly tap it, and then the camera has to see it. So let's see if it works. Okay, you should have won. The robot should have won, but yeah, the lighting is kind of bad for these cameras.
Yeah, good. Okay, so this is one AI application.
Yes.
That run a module. Yeah, is the model is saved here to connect to the camera and then detect what is my hand doing.
Exactly. So there are actually two neural networks. The first one is for segmentation, and the other one is to actually figure out the shape of your hand, right? And then it just takes the feed from the camera, passes through those applications, and then everything runs inside the container on Horizon OS. So we can even remote update it if we really want.
Okay, cool. So how about the balance? Like I see it's like it balanced very good. So I'm trying to crash
actually, that's a very good question, because the balancing is actually, if we technically speak, not so good. We actually made it so it has a little bit of a swing. Otherwise, if we really tone the control down, it would be completely static like this.
Wow.
So we realized people actually like having the robot swinging a little bit like a toy.
Exactly,
so we made them swing.
To be like coming in, out, in, out. Okay.
Yes, exactly.
Okay, cool. But so the balancing comes from different microcontroller, you told me, yeah?
Yes, the balancing comes from the M4 core.
M4 core?
Yes.
It is system on module or what?
So inside the system of module, you have the application processor, and you also have the M4 core, which is a Cortex M4, right? An ARM processor, basically. And they run completely independent from one another. So you can have one turned on and the other one turned off, but the balancing itself, it doesn't come from the application processor. Like Linux.
So they are two separate stuff here.
Yes, Linux doesn't know about the
motors.
The motors. It actually does know, because you can control them through Linux, and we actually have this done, but you don't have to.
Yeah. Okay, amazing. Yeah. Very wonderful application. Maybe I will try one at home. Let's see.
Yeah.
Thank you so much.
Absolutely.
Okay, cool. So looks like there is a real application here in system on module. That looks amazing. Can you tell us a little bit about what is it?
Yeah, sure. So we use the Toradex IMX7 module to control our stair climbing wheelchair. So this is basically an electrical wheelchair that also combines a stair climber. And you can drive around with it in balancing mode. That means you are actively balancing like a Segway on one axis, which gives you a lot of flexibility. And you have also a seat level function that elevates you and also can put you down. And if you go to the stair climbing mode, which is quite easy, you can change modes via the smartphone app or via the control panel. You can drive easily up and down the stairs. So I would say, let's give it a try.
Oh yeah, cool. So maybe I can try it out, but before of that, so these, for whom would be these helpful?
This is basically interesting for all patients that cannot walk by themselves anymore or cannot climb stairs by themselves. So, and it is a combination of a classical electrical wheelchair and a stair climber. So it brings those products together into one.
Yeah, looks amazing. So I would like to try it out. So maybe you can tell me a little bit about what should I do. And so the first step would be, I think, sitting.
Yes, take a seat. Actually, it is quite easy. Here you have the menu with the different modes. We are now in the park mode, which is shown by the green P. And now to drive up the stair, we switch to the stair mode, which is indicated by the symbol here. And you can reach all the states by just selecting via the joystick. So if I do this, it now shows you it will transition into the stair mode. And now you have to confirm that you really want to do this by activating the joystick. So if you just push the joystick now, it will do the transition for you in any direction. Yes, like forward or backwards. Just keep. keep pulling or pushing.
On the camera, yeah.
Yes.
Oh, yeah.
Don't worry. Yeah, just a little bit more. Yes, there you go. And now you are attempting the first step. And what the wheelchair does, it will always level you. So you will be always...
Does it matter in which direction do I position the joystick?
Yes, now it matters when you're on the stair, it matters. You have to pull backwards now to go up the stair, and later on to go down you have to push forward again.
Okay, but so if I push it to the left side or to the right side,
nothing will happen now. If you push to the left or right, it will just ignore the input as long as you're on the stair. And it will keep you aligned perfectly on the stair.
Now I'm trying to go up. I like that it's very smooth, so I don't feel that much, but I'm doing a lot of stuff here. But be careful with your hand, yeah.
So
from the other direction. So now I'm in the very top and I'm balancing.
Just a bit more. A bit more.
A bit more to the back.
Yeah, right there.
So I trust technology.
Yes, there you go.
Enough. Okay.
And now you can basically reverse and go down.
So
just push the opposite direction.
Okay. So now let me. So now when I put it basically to the other direction, I go up again and then start to bring me down slowly. Well, I trust technology.
She's not in the university. No,
well, it's a good feeling.
So she's head of science.
Bring me up and then slowly but surely.
So then, since we did not able to live
but bring me then down. Well, it works very smooth. I like this. And then back to the ground. And then if I want to come down, I think...
Yeah, you have to drive a bit more forward because you're still on the edge.
And then it is
so
automatically detected.
just a bit more forward. Yes, there you go. And now we can switch again to park mode. And then to the side. And then it will level you down.
In the park.
So you can easily get out.
Yeah, amazing. This is a very cool experience. Yeah, thank you so much for
You're
this.
welcome.
We should that a lot of people, plenty of people are willing also to try it. I would advise to do it. Yeah. And yeah, thanks.
Thank you.
Wonderful, very cool experience. So it's coming now to the end. Thank you so much for watching the video to the end. If you have any questions, please write in the description below. And give me one like and please subscribe to the channel because there will be more and more videos in this field.